Yes, in this video we are going to discuss section 1.2 of the readings, which talks about what are called slope fields. So a slope field is going to give us a way of visually representing a differential equation. It's going to be like our graph of a differential equation. And what we'll see is once we can get a general picture of a differential equation, it's going to help us come up with nice approximations, graphical approximations for solutions to a differential equation, even if we haven't thought about how we can specifically solve them just yet. So let's consider this differential equation, dy dx is equal to y. And let's say, for example, I want to know what does the solution to this differential equation look like, let's say, at the point 0, 1. So let's say 0, 1 is approximately over here. So when I plug x equals 0, y equals 1 into the right side of this differential equation, well, the x doesn't go anywhere. We plug y equals 1 in over here, and we see that we would get a slope of 1. So what that tells me is, regardless of what the solution through to the differential equation through the point 0, 1, I know that at this instant the solution is going to have a slope equal to 1. And then we can repeat this for other points. So for example, when x is 2 and y is 2, then that means I would plug this into the differential equation. The x, again, this differential equation doesn't depend on x, so the y value alone is going to determine what the slope of the solution through the point 2, 2 is going to be. And that's a quick calculation that we would get dy dx is equal to 2 over there. So at the point 2, 2, let's say that's approximately here, we're going to get a line segment whose slope is 2. So it's going to be positive and a little bit steeper than the one over here. And we could keep on repeating this at other points. So for example, if I wanted to look at what is the slope of the solution through the point at minus 1, then that would give me again, I would just take the y value, plug it into this differential equation, and I get minus 1. So that tells me that over here, at minus 1, the slope is now negative 1, so it's going down. And we can repeat this at every point in the xy plane. And let's see what this looks like now more completely. Looking at the graph, we can see that for all of these points along the line y equals 1 that all have the same y coordinate of 1, they're all going to have the same slope of 1. All of these points that have a y coordinate of 2, the solution through all of these points is all going to have a slope of 2. And so as we've been saying, this is a really special differential equation because it only depends on the dependent variable y. It does not depend on x at all, and that's why we're seeing this behavior that the slopes of the line segments along each horizontal line where the y value is the same are parallel. And so when a differential equation has this property that it doesn't depend on the independent variable, we say that the differential equation is autonomous. Okay, and so again, autonomous means it is independent of the independent variable, which in this case is x. Okay, so the differential equation only depends on y, so it's the y coordinate of each point alone that's going to determine the slope. That's certainly not going to be the case always, as we'll see shortly. But we get some really nice special properties from autonomous differential equations that we'll take a look at more in depth in the next section. So let's look at what this is going to look like when it's complete. So now we've got a differential equation that I've filled in at tons and tons of points over here. And now what's the use of getting a differential equation, a slope field for a differential equation, is, well, now if I wanted to know what is approximately the graph of the solution of the differential equation through the point at 0, 1, these line segments tell me approximately the steepness of that, so I can get a pretty good picture of what the curve looks like through that point. If I wanted to think about what does the solution look like through the point at -1, -1, let's just say that's approximately over here. Again, I would do the same thing and just sketch out a curve following these little directed line segments that we have in the slope field. Okay, so now let's take a look at this next example. Well, now we have two different differential equations. So I've got one differential equation, dy dt is 2 minus y. So notice the independent variable has now changed to t. And over here we have dy dt is t divided by y. So this differential equation, because it doesn't depend on the independent variable t, is autonomous. This differential equation does depend on t, so it is not autonomous. And if we want to match each of these differential equations to one of these possible slope fields down below, we just solved it, right? Because this differential equation is autonomous. Its corresponding slope field should have the property that the slopes of the line segments are parallel, they're the same for the same fixed y value. So each time I move across a horizontal line on this slope field, we can see that all of the line segments have the same slope. So that's a good reason for this autonomous differential equation to match the slope field on the left. This differential equation, it does depend on the independent variable, and now we can see as we move through this slope field, the line segments are changing their slope both when we change t. So over here, if we fix a y value and we change t, these slopes are changing. When I fix a t value and move down a vertical line, we can see that for a fixed t value, when we change y, the slopes are also changing. So because this differential equation depends on t and y, we're seeing that the slopes in the slope field are changing when we change both y and t. So by that process, we've matched up each of the differential equations with one of the slope fields. And then, just like in the previous example, what these slope fields allow us to do is get a good sense of what the graphs of the solutions look like. Even if we haven't thought about what the formulas for the solutions are, we at least can sketch graphs for these solutions. So for example, when y is 0, when y is 1 and t is 0, so maybe that's about over here, this differential equation, the solution to that differential equation is going to have a graph which is approximately that shape. When y is 3 and t is 1, that's somewhere between here and here. And so that differential equation is going to have a solution that looks like that, more or less, through that point. And we can do this as well when y is 0 and t is 1. Maybe that's about over here. I can follow these line segments. And we can do the same for this slightly more complicated slope field on the right. That is when y is 1 and t is 0. Maybe that's about here. We get a good idea of what the shape of that solution is going to look like. When y is 3 and t is 1, maybe that looks like this. And when y is 0 and t is 1, we can sketch this solution like that. So here I'm just giving a kind of general approximation for these solutions. And one last thing that I want to comment on is we could have matched these up using some other properties of the equations for the differential equations and the properties of the slope field. So for example, for this differential equation, we can see that when y is bigger than 2, dy dt would be negative. And so we can see that for any y value above 2, all of the line segments here have negative slope. And when y is less than 2, all of the line segments have a positive slope. And we can't really see it, but when y is exactly equal to 2, we are getting that the slope dy dt should be 0. So we would have a bunch of horizontal line segments through any point that has a y-coordinate of 2. And we've got properties for this equation over here, namely that at any point when t is equal to y, so for example on the line y equals t, all of these slopes are 1. When t and y are same magnitude but differ in sign, then we can see that these slopes are going to be exactly -1. So there are other properties of the equations that we can check to see that they're represented in the slope field as well.